Kristen Duffee. Integrate probabilistic computer using voltage control magnetic tunnel junctions as its entropy source. So thank you very much, and please go ahead.
Thank you. I'd like to present some of the work we've been doing at Northwestern with some of our great collaborators around the world. So to touch briefly on the Ising model, as I've been corrected, it's meant to represent a spin lattice traditionally. And it has this quadratic form, as you can see on the right there. And originally it was just a one-dimensional and then two-dimensional. And then there was some discussion of three-dimensional lattice representation. But in general, for optimization purposes, we do not care about this geometric constraint. So we can imagine that we can have arbitrary coupling between spins through our coupling matrix. And ultimately, we can encode many interesting problems into this format, such that their solution corresponds to the ground solution of the Ising model. And there are many ways to find this ground state solution that have been presented this week. But the one that we focus on is termed probabilistic computing. So probabilistic computing is somewhat of a discrete method of doing this. The spins have a single state, either up or down, and then they transition between the state instantly, typically at discrete time steps. And if you use the update rule in the bottom right, which is determined through a simple sigmoid S curve based on the influence of the other connected spins, or P bits, then you can get an update function that looks like the graph on the right there. This update function is, of course, temperature dependent. But if you select an arbitrary spin, update it, and then move on to the next spin, and you repeat this process over and over, you form a Markov chain of different states of the system as a whole. And if you do this enough times, you will converge to a stationary distribution that models the Ising function that we originally started with. Of course, for optimization purposes, we do not care too much about this distribution itself. We simply hope that in doing so, we find the ground state at some point. Okay, so Jordan Athos talked about this more in depth, but just as a refresher, we used magnetic tunnel junctions, which have two magnetic layers separated by some tunneling barrier. One of the layers is free to switch between two states. In the parallel state, it has a low resistance, and in the anti-parallel state, it has a high resistance. So it is very easy to read out in circuitry. And these are VCMA MTJs, which means that we can apply a voltage pulse to annihilate the energy barrier between these two states. And when we remove this voltage pulse, we find ourselves in a random state. So to read this out, we implemented the circuit there in the top left. It is a relatively simple circuit. We have one write path and one read path. We send a writing voltage pulse, and then immediately after, we can read with a smaller voltage pulse. And then this, because it is a bistable resistor, we can read this out as a binary value. So if we do this repeatedly, we have a random bit stream with 50% probability. So we implemented this on a PCB board there in our top right, which is connected via normal electrical 5-cent wires to our ASIC we also designed. The ASIC has two components. The one on the bottom is a RISC-V CPU. This RISC-V CPU came with the wafer service we were using. So we didn't really want to use it. It is only used to transfer our random bits from our PCB to our probabilistic Ising machine design area, which is that on the top. Here are some block diagrams of the various aspects of the system. The system as a whole is here in the bottom right. Here's our CPU, here's our design area, and here is our MTJ components. Here's the probabilistic Ising machine block diagram. Our probabilistic Ising machine is composed of what we are calling the probabilistic logic unit, and then a number of p-bits. The probabilistic logic unit takes a bit stream, we use 16 random bits, and converts it from what is essentially a uniform random number into the sort of sigmoidal distribution we need for probabilistic computing. Then each of the p-bits will compare their input value, which is based on the influence of their neighbors, to this random number. And in doing so, they can update their states either to the +1 or -1 state. And highlighted, you can see the corresponding aspects of the equation that are implemented by each portion of the circuit. But what problem did we implement? So to do this, first I want to talk about the concept of invertible logic gates, specifically probabilistic computing invertible logic gates, as there are a number of related concepts. But you can imagine virtually any typical logic gate has some inputs and some outputs that can be represented as electrical nodes. If we imagine these nodes are p-bits, we can select a coupling matrix to couple them that will allow them to behave like those logic gates themselves. But they do so in an interesting manner. In selecting these coupling matrices, you have to generate a probabilistic computing state such that the ground state of the network is equivalent to the valid states of the original gate. So for an AND gate, that is a 0, 0, 0 case, the 0, 1, 0 case, the 1, 0, 0 case, and the 1, 1, 1 case, of course. And if you let this network of 3 p-bits sit on a desk somewhere, it will oscillate between these 4 states primarily. But you can do something interesting in that you can grab any of the p-bits and clamp them to a specific value, either the +1 or -1 value. If you clamp the input p-bits, then the output p-bit will go to the corresponding output state. But it also works the other way around. If you clamp the output p-bit of our invertible AND gate to the 0 state, then the inputs will switch between their 3 valid configurations. And these are kind of interesting by themselves, but they become useful when you chain them together. You can compose an arbitrary number of these invertible logic gates together to create an invertible circuit. And the circuit has the exact same properties of the gates themselves. So if you imagine a multiplication circuit, it can act as a multiplier if you clamp the input p-bits to a corresponding binary string of 2 numbers we're trying to multiply. But it can also act as a factorizer if we clamp the output to a number we want to factor. And there is a related version where you clamp one of the inputs and the output, and it acts as a divider. And here are the probability distributions of all 3 modes for a small problem. But of course, multiplication is very easy to do on a CPU. So is division. So really, we care most about factorization, which we selected as a representative problem here. So you can see our probability distribution again in our bottom left here. You can see the proportion of times that we are in the quote like correct state that factored the number based on our starting and ending temperature using simulated annealing in the top left. And on the right is one trial where we're lowering the energy of the system indirectly by lowering the temperature. And it does converge to our ground state here. Of course, that was a small problem. We were limited in experimental data using the MTJs because of our RISC-V CPU. The I/O in that configuration was a bit slow. But we used a pseudo-random number generator on a second ASIC with the same design to factor a slightly larger number there. And in this case, we are using the trick in that if we ever encounter the true solution, we stop the simulation. Because of course, a lot of these problems are easier one direction than the other. Factoring a number is hard, but checking two factors is very easy. So one time. Okay, so the majority of what I've presented so far is in this work right here that is currently on archive, with some concepts from this first paper up here as well. If you have more interest in it, I encourage you to check them out. But I also wanted to talk a bit about something else we are working on. So of course, in general, we can map many problems into the Ising model. But not all problems map naturally, to speak very vaguely there. We can imagine that there are certain forms of probabilistic variables that map a bit better to the problem, and which might result in better performance. But first, let's talk about where problems are not mapped ideally, in my opinion. In one such case, you have the representation of categorical variables. This arises very naturally in a large class of problems. Graph coloring is one of them, for instance, but set partition is another. So for these categorical variables, you start with some variable and you assign it one of a collection of values. So graph coloring, these would be your colors. Set partition, these would be your various sets you can go to. And for when there are only two options, it maps naturally. But when there are more than two, you have to use this one-hot encoding representation. So for each variable, you have a number of p-bits equal to the number of possible values. So if you have n variables and d possible values, you have n times d p-bit representation. In each collection here, you have exactly one p-bit that is in the up case, which encodes the value of the variable. Of course, this leaves some room for error. If no p-bits are in the up state, the concept of the variable is undefined. And if more than one variable are in the up state, then it is similarly undefined or underdetermined. And so the way this is traditionally combated is by having some sort of energy term that forces the system to have this one-hot encoding representation. And this works well to an extent. However, if you are using a probabilistic system, you have a finite thermal noise. And so for large systems, you will always have some p-bits that are in the wrong state, and you can't directly read out your encoding of your problem. Here on the right, you can see that the proportion of valid assignments out of our total state space decays exponentially as we increase the number of categorical variables, even for a very small number like 20 here. So another way we can encode these variables is with something we are calling a probabilistic isotropic d-dimensional bit, or p-dit. It is similar to a p-bit, except instead of having two possible states, you have an arbitrary number of them based on the variable we are trying to represent. This is similar to the concept of the vector Potts model. However, I would like to draw the distinction. Whereas the vectors Potts model, as you increase the number of possible states, you have certain states that are closer to each other than others just based on their angle. Whereas in this case, we can imagine all these states are equally orthogonal to each other. And we can do that because this is ultimately a discrete model that we don't have to use some sort of oscillating system to represent it. So our update function is there on the bottom. It updates very similarly to a p-bit, except you're considering more energy differences because we have more possible states. Okay, so on an ASIC, which I will talk a bit about more later, we considered a small 3-partition problem of size 14. In this problem, you have a set of numbers that you are trying to subdivide into 3 partitions, such that the sum of each set is equal. On the left here, we see our equation to encode this problem in using p bits in the Ising model. And on the right, we have the equation for the isotropic p dits. So this equation on the left is longer, but that is not innately an issue. But what is somewhat of a challenge is that we have this constant c that determines how much we are prioritizing the one-hot encoding constraint relative to the objective of our problem here. We sweep this here in our top left graph. If we have too low a value, then the system does not want to realize this one-hot encoding, and oftentimes we are in an undefined state. But if we have it as too high of a value, then we just stay in the same one-hot encoding state the entire time. So there is some optimum, but it's another parameter that we have to optimize for. In the middle, we have a temperature sweep as well, but on the right, we can compare the performance between the p-bit and the isotropic p-dit case, and we see better performance in the p-dit case. We also explored a larger problem using these isotropic p-dits, a 6-partition problem with 100 or 1,000 numbers. And we can see that we continue to converge down to a low energy state as the system grows. But I also wanted to talk about a different class of problems, integer linear programming problems. This is a language in which many types of real business optimization problems are represented in. You have a series of constraints that are linear, and then you have a linear objective function. But there can be quite a difference in the range of the different integers we are representing. Of course, we can map these problems into other MP representations, but that does add some overhead. So it would be nice if we could address these in its natural form. So there is a way to represent integer variables using p bits. This is typically done using a binary encoding format. So you have one p bit that represents the ones place, one p bit that represents the twos place, and so on. And this does work, but it has some interesting behavior that is not immediately obvious, I believe. So in the top left, we have the energy graph of a simple 2-variable problem. And in the bottom, we have the sampling frequency for a p-bit implementation of this. Of course, you would imagine that the p-bit would sample along the entire energy value, but we don't see that here. And this is because going from the x2 equals 0, or x2 equals -1, sorry, to the x2 equals 0 case, in the original problem is energetically favorable. But in the map problem, we have to make 4 spins and move through an energetically unfavorable state. Now, of course, if we increase the temperature or we ran this for longer, we would make that jump, and the limit behavior would look exactly like our top graph. But I mean to use this example to show that by using a binary encoding, we are introducing an energy barrier that is not there in the original problem. Okay, so what else can we use? We use something called probabilistic integers. So these are one-dimensional units, but they can go for a longer range than -1 to 1. We can go from A to B arbitrarily. Particularly, we look at the case where each update, you can either stay in the same value, increase by 1, or decrease by 1. This is in contrast to the isotropic p-dits, which I discussed earlier, in which case all these states were orthogonal. In this case, a state of 2 is along the same dimension, but more than a state of 1. So, of course, with the same toy problem, the p-int system does not have any issue in exploring our energy value. But I wanted to look at some problems as well. This is the exact change problem. Of course, nowadays they force us to pay with credit cards. But if you wanted to generate change using a weird value of coins, you need to use these weird values because with any reasonable system, it becomes very trivial. But using a weird value of coins, the problem is a bit difficult. And then we implemented this using p bits and p ints. And you can see a temperature sweep there on the left. This is included just to show that we aren't picking some temperature where the p int system works better than the p bit. The p int system actually works better across all temperatures compared to the p bit case for this problem. And on the right, you can see the success probability in finding the ground state as we increase the trial length. Okay, so here is the application-specific integrated circuit design. It looks very similar to the first design I talked about. So particularly, unfortunately, we did not use MPJs for this. We used an onboard random number generator, which allows us which allows us to avoid having the issues where our MTJs would die. And we can run it much faster, not having to go through the IO of the RISC-V CPU. But in this case, it is still a very similar architecture, and we could implement MTJs if we wish to, and which we are trying to do for future works. So we still have the PLU, or probabilistic logic unit, which implements the sigmoid shape, which we need to do any sort of probabilistic computing. And then we have a number of these probabilistic elements. These probabilistic elements can act either as a p-bit, a p-int, or an isotropic p-dit for this circuit. And then we get an update of one of these probabilistic elements every 2 clock cycles. But we didn't want to constrain ourselves to this ASIC design. So we looked for a different problem. And the problem we decided to choose was the integer quadratic programming problem. This is similar to an integer linear programming problem in that the constraints are still linear. However, the objective function becomes quadratic. And if the equations you choose make the problem convex, which it does in this case, it becomes non-trivial to solve using existing solvers. So we had this problem, and we looked at the performance of a number of software CPU state-of-the-art solvers, which were included in the GAMS solver suite. And we saw a variety of performance out of them. So within a 10-minute timeout, we saw that 2 of our solvers did not find the ground state solution at all, which is not great for them. But these solvers are very wide solvers, so I don't want to talk too badly about them. And in fact, 2 of them did find the ground state solution after around 20 seconds. But our FPGA implementation of our probabilistic integer solver also found the ground state solution, and it found it much quicker than the solvers. In this case, about a 64x improvement in time to solution. Of course, the p-integer FPGA case is on an FPGA, but I do want to specify that the FPGA was only running at 50 megahertz. It's a very simple FPGA, while the software solvers are running on a CPU at 4 and some change gigahertz. And we will be trying to look at FPGA to FPGA comparison going forward. So I guess I finished a little bit early, so plenty of time for questions.
Thank you very much. there are questions? There are several questions, so yes, please.
Yeah, thank you.
Very nice work. When you do ASIC,
Yes.
which part is delegated to the outside, or is everything the whole pipeline is implemented in the ASIC?
Yes, so when we are running an ASIC problem, we write C code that runs on the RISC-V CPU. But all the C code does is it initializes our initial temperature, our ending temperature, and the sweep parameters. Everything runs on our design up here. Yes, it is fully digital, yes.
Okay.
You talked about the p-bits with magnetic tunnel junctions, but then you also talked about the p-dits and the p-ins.
Yes.
How do you realize this multifunctionality with them?
Yes. So this is for the p-int case. This is implemented digitally. So we are calculating it using a series of lookup tables. But for the p-int case, we use exactly this update scheme. So we consider the same I value, which is the influence of neighboring p-bits. In this case, p-ints actually. On the p-int, we are considering updating, as well as self-coupling term. For the p-dit case, it is similar. Except we are considering the energy difference between each pair of states. Yes, so we only use the VCMA MPJs in the first case to generate random numbers. And these are not weighted random numbers. They're 50-50 because we believe that scheme is a bit more scalable. Of course, there's very good work showing otherwise as well.
Computer programs that you solve, how are you doing constraints?
Like how are we mapping it?
Yeah, where you or did you implement something particular with pivots?
Yeah, so the let's see. So the you can represent this as a cubo formulation. Yeah, okay.
Have you looked at one of the second or
Yes, so our collaborators are specifically this guy, if you want to talk to him later, but they are working on a traveling salesman problem. Yeah, we are very interested in it.
there another question? Well, if not, let's take speaker again.